All right, guys, this is gonna be the last video for chapter 7, looking at the sampling distribution of a mean. This first page is just looking at an activity that I want you guys to look at on your own. It's this little website. You kind of follow these directions, and we'll look at this again in class. We kind of see what happens when you do that. So again, same as last time. I'm going to talk about some big definitions, and we'll kind of do the problems in class together. But yeah, we're just going to look at some big definitions so far. So first thing is what is the mean of your sampling distribution of means? So we're going to write x bar as a sample. So x bar is equal to mu of x bar, which is equal to mu. So again, unbiased estimator. So we know that the sample mean is going to be equal to the population. Okay. Under standard deviation of x bar is equal to sigma over the square root of n. And again, same thing. Take a look at what happens as n increases, right? This fraction is going to get smaller and smaller, right? Because as n gets bigger, then the denominator is going to get larger. And so then you're dividing by something big, and therefore your fraction is going to get smaller. And so as your n gets larger, you're going to have less variability. And again, same thing as always, we need to check the 10% condition. This is your independence condition, so n needs to be less than or equal to 1/10 of big N. So what's the shape of your sampling distribution of the sample mean? So in the last video, I talked about how if you check the n times p and n times 1 minus p, if those are both greater than 10, then it's going to be normal or approximately normal. So here we're going to have a couple scenarios. So the first one is if the population distribution is normal, this is the easy one, then the sampling distribution will also be normal. Which kind of makes sense. If your population is normal, then your sample should be normal. And then it's going to lead to my next point where, so right now, so if population is normal, then sample size does not really matter. But if population is not normal, then sample size will matter. We're going to talk about this in a little bit. Right. So same as before, you've got this definition here for mean and standard deviation. So we're going to talk about the state plan to conclude again in class. But see if you can go ahead, see if you can calculate the mean and standard deviation for this problem down here at the bottom. And again, we'll look at this problem in detail in class. See if you can find the probabilities. And yeah, we'll go from there. What's one thing you got to make sure you remember? That most students forget to divide by root n on the denominator. I was just going to lead to a wrong standard deviation. So make sure you do that, and make sure you check your conditions. Make sure you're kind of doing this before you kind of go into your problem. And this next question here, I posted that video for your discussion about the Galton board and how, if you kind of keep taking these random processes and then you end up with a normal distribution as your sample size gets larger and larger, that's essentially what the central limit theorem is. Okay, so this next part here is talking about the central limit theorem, which is probably one of the biggest things in stats. So here I'm going to talk about, so when the distribution is not normal, sample size matters. So I kind of mentioned this earlier. So we need to look at and use the central limit theorem, which I'm just going to call it CLT from now on. So the CLT says that when n is large, sampling distribution of x bar is approximately normal no matter the shape of the population distribution. Now, here, a little caveat to this is that the more skewed the population distribution is, the larger n needs to be. All right, and so typically what we say that if n is greater than 30, we can use the central limit theorem to assume normality. Right. So if your sample size is larger than approximately 30, okay, then we can assume normality. And then again, we can use our best friend z-scores. Right. So that's kind of the whole point of this, is that once we determine that the distribution is normal, then we can use z-scores to then calculate some probabilities. And that's exactly what the next question is looking at, is that here we're telling you the distribution is skewed to the right. However, what we can do is, because we know our sample size is 50, we can assume normality, and then we can kind of go from there. So again, see if you can calculate the mean and standard deviation of this problem here. And again, it's something that we'll look at in class with the state plan to conclude. Last little bit of this video, and kind of get a little wrap up here. And again, we'll go through all the problems in class together. So briefly to explain what each of the symbols mean. So kind of go through this. So the first one, mu, is your population mean. Okay. Next one, sigma. I'm just going to draw all these out first. P and x bar. And then p hat, mu x bar, mu p hat, sigma x bar, sigma p hat. Okay, so what do each of these mean? So the second one is your population standard deviation. I'll write this down in a second. So your population standard deviation. P is your population proportion. N is your sample size. X bar is your sample mean. P hat is your sample proportion. Mu of x bar is your mean of the sampling distribution. Okay. Mu p hat is the mean proportion. So proportion of sampling distribution. These are your last two are your standard deviations of sampling distributions. Okay, so another way, kind of summarize this. Your first three here, these are all population. So this is population. The next three, these are your sample. And then the last four are your sampling distributions. So just kind of keeping track of all those symbols is kind of going to be important, so you kind of know what each thing is talking about. Sampling distribution. So just kind of keep track of those symbols as you go along. All right, last thing here, compare, contrast p hat and x bar. So I'm just going to draw a line through the middle here. All right, so for x bar, I'm going to talk about a couple things here. So shape is normal if population is normal. If population is not normal, need CLT, so large N, right, greater than 30. And the center is equal to mu x bar, subscript x bar, which is equal to your population mean, so it's equal to mu. Your spread is equal to sigma over square root of n. And again, make sure you check conditions. You have to check normality, and you need to check that small n is less than or equal to 1/10 of big N. Okay, compare that to p hat. We have shape. We have normal if np is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So those are your kind of conditions. And you always need to check that. And your center. And so your mu underscore p hat is equal to p. So whatever your population proportion is the same for your sample because it's unbiased estimator. Your spread is equal to the square root of p times 1 minus p all over n. And again, need to check 10% condition, which is the last one we checked over on the other side. So it's kind of the difference between the two. Keep track of those. And again, make sure you're just reading the problems when you do these, right? Are you talking about proportions? If you're talking about percentages, you're using the p hat side. If you're using means, you're looking at x bar. So again, that's the end of these notes. This is all of chapter 7. Like I said, we're going to go through the problems in class. We'll look at some activities. These are kind of just like a good little Spark Notes version of the notes. As always, if you have questions, let me know. But have a great rest of your day.